Hi, I'm Josh, and this is Electronics Unscripted, where we take an intuitive and unscripted approach to DIY electronics. Recently, I was creating a circuit, and I just kind of mindlessly put together an RC circuit, so a resistor and capacitor in series, in order to remove a DC offset from a signal. So I needed an audio output signal, and so that signal needed to be centered around 0 volts and very above and below 0 volts. Well, I kind of understand why that happens. I know that it's a high-pass filter, so it removes low-frequency stuff and so forth and so on. But I didn't really understand the mechanism of that. What I wanted to do was to look at an RC circuit in a circuit simulator. What I have here is a simple RC circuit. So I've got a 10 microfarad capacitor and a 1K ohm resistor. At the top, I've noted the time constant of these particular values. So that time constant, called tau, is the resistance times the capacitance. And here we have a 10 microfarad capacitor times a 1 kilo ohm resistor. That means our time constant, tau, is 10 milliseconds. Over time, if you apply a voltage, the capacitor charges up, and it takes some time to do that, and tau is basically a measure of how much time that will take. So for tau equals 1, or 10 milliseconds, you reach about 63% of the max voltage. For tau equals 5, or about 50 milliseconds, you reach 99% of the maximum voltage. So we have a voltage source of 5 volts DC with 0 offset. So when we run this calculation, we just basically apply 5 volts to the RC circuit and we see what happens. So let's go ahead and do this, and we can see that the capacitor slowly charges over many milliseconds, and if we look here, scrub along to about 10 milliseconds, we will find 3.185 volts, which is our 63%. The simulation matches the theoretical prediction of how quickly this particular RC circuit should charge. If we let it run a little bit longer, out to about 50 milliseconds, and stop it, we can see that we've got about 4.967 volts, matching the prediction almost exactly. What would you predict would happen if I increased that resistor here from 1 to, say, 10 kilo ohms? That's going to make our R times C, instead of 10 milliseconds, 100 milliseconds. So let's give that a shot. And now you can see that the voltage is ramping very, very slowly. Let's take a look. At 100 milliseconds, yes, we're at the 3 point. So we've done exactly that. But if we ran this simulation out to 500 milliseconds, we get up to 99%. So let's go ahead and do that. We're at 4.9 volts at roughly 500 milliseconds. Let's put this back to 1 kilo ohm and explore this a little bit more. What happens if we replace this with a time-varying AC source or a square wave? Let's go for a square wave, but let's calculate it such that it's on for 1 tau and off for 1 tau. On for 10 milliseconds and off for 10 milliseconds. So that would be a period of 20 milliseconds or 50 hertz. Let's go ahead and see what happens when we do this. We can see that square wave up here is on for exactly 10 milliseconds. You can see it starts to charge up, and then as the voltage flips to negative, it starts to just discharge the capacitor. So if we go along here and look at 10 milliseconds, we do see that it did charge up to that 3.15 volts that was predicted based on that time constant. But notice something interesting about this. The input waveform is a square, right? And the output waveform here is kind of a triangle, and it's a lower voltage. If we let this run for a little bit more, it even goes to a little bit lower voltage. So it goes to 2.3 volts. So we've attenuated that input voltage by about half. What this capacitor is doing is it's acting as a low-pass filter, and it's attenuating higher frequencies. And then conversely, the resistor is acting as a high-pass filter, and it's attenuating lower frequencies. And that's not quite apparent yet, but if we start to up the frequency, we can start to see that a little bit more. So let's go up to 100 hertz. You can see the resistor's output is starting to look more and more like the square wave input, and the capacitor is more strongly attenuating it, so it's now down to 1.2 volts. Let's go to 500 hertz. you can see that the capacitor is now just this little tiny wiggle in the millivolts range. So the capacitor is very, very strongly attenuating this higher frequency, where the resistor is now starting to look very much like the input voltage. So the resistor is going from 5.25 volts to negative 5.25 volts, and it's starting to look more and more like a square wave. And let's go ahead and take this up to 1 kilohertz. The capacitor has almost fully attenuated this higher frequency, while the resistor is doing the exact opposite. It's passing higher frequencies and attenuating lower frequencies. Let's take a look at a low frequency limit. This is 500 millihertz, or basically a half a hertz, like a cycle every other second. The capacitor is now very nearly mirroring the source voltage, 5 volts positive to 5 volts negative, and it's almost a perfect square wave with a little bit of that charging time. That's because the cycle time of the voltage source is so long compared to this time constant of 10 milliseconds. It really doesn't take long for that capacitor to charge up relative to the time that the voltage is positive or negative. And then if we look at the resistor isn't blocking the low frequency signal perfectly. There's these weird spikes, but we do see that the resistor is floating around 0 most of the time. So it's effectively blocking most of this very low frequency signal. Let's go back to our 1 kilohertz signal and get back to the problem that got me here in the first place. I had a signal with a DC offset, and I just kind of blindly threw it at an RC circuit, knowing that it would block that DC offset. I'm going to put a 3 volt DC offset onto my voltage source. It's kind of cool. So the capacitor charges up to that 3 volts and has the wiggle that it had before, but now it's doing that superimposed on top of 3 volts. Let's watch that again and watch what happens to the resistor. So at first, the resistor is kind of perturbed. It's floating above. It's not a pure AC waveform. It has some of that DC offset, but as the capacitor charges up, the resistor goes back to the same way it was before without that DC offset. After that capacitor charges up, the DC offset can no longer drive current across that resistor, and it's just the AC waveform on top of it that's driving current across the resistor. So only that AC waveform can impact the voltage across the resistor. The voltage across the capacitor is doing the exact opposite. It's actually passing that DC offset almost perfectly and blocking the AC waveform. So another way to think about this intuitively, a DC offset is kind of the limit of a low frequency. It's a 0 hertz signal effectively. And so we would expect the capacitor to pass that almost perfectly, which is what we're seeing here, and we would expect the resistor to block it almost perfectly because of the nature of the filtering that they're doing. I'm Josh. This is Electronics Unscripted, and thank you for watching my short on RC circuits.